Okay, so the first example we're going to look at where logs occur in chemical calculations is the Nernst equation. And the Nernst equation determines the cell potential E based on the standard cell potential E0 and the ratio of oxidized to reduced species present in solution, according to the equation given below. And you see here this has a log term in it. It takes the log of the ratio of concentrations of oxidized to reduced species. The Nernst equation can also be written as E is equal to E0 plus this value times the natural log of the oxidized to reduced species ratio. And you see here the only difference between the top equation and the bottom equation is this number 2.303 and the base of the log. In the top equation is log to the base 10, in the bottom equation is log to the base e. And we can interconvert between the two by using this number 2.303. You can check on a calculator for any number. The natural log of x is 2.303 log to the base 10x. Experimentally, this is used by relating the Nernst equation to the equation of a straight line, y is equal to mx plus c. So if we measure the cell potential E for various different ratios of oxidized to reduced species, for example the iron 3 plus to the iron 2 plus ratio, well then we could determine the standard cell potential and the number of electrons transferred. If we take the Nernst equation in this form, the log to the base 10 form, well then if we plot E against log of the oxidized to reduced species concentration ratio, you can see by relating this equation to the equation of a straight line y is equal to mx plus c, the y-axis intercept is going to be equal to E0, the standard cell potential. M, the slope, is going to be 2.303 RT over NF, and therefore that will allow us to calculate N. If we take the Nernst equation in the form with its natural log, well, I'll still plot E against the natural log of oxidized to reduced species concentration ratio. The y-axis intercept will still be E0, but in this case the slope will be RT over NF. So it depends on which one you choose. The second example we'll look at is Gibbs energy. And Gibbs free energy is related to the equilibrium constant according to this equation. So if we know either K or delta G, this equation allows us to interrelate the two. So let's say we know the value of delta G for a reaction. We can calculate the equilibrium constant very easily just by rearranging this equation. So if delta G is minus RT ln K, well then if I divide across by minus RT, I get an expression for ln K, and then to get the anti-natural log, effectively we want to get the exponential. So K is equal to exponential of minus delta G over RT. The third example we'll look at, and we'll work out an example for this one, is the Classiest iperion equation. And this relates the vapor pressure phase boundary, the temperature and pressure at one point, to the temperature and pressure at another point. So if we know pressure P1 at a certain temperature T1 on the vapor phase boundary, we can relate that to the vapor pressure P2 at another temperature T2 according to the Classiest iperion equation. This says that the log of the ratios of vapor pressures, P2 divided by P1, is equal to minus the enthalpy of vaporization over the gas constant upon 1 over T2 minus 1 over T1. So I'm going to look at an example now where we're given the vapor pressure at a certain temperature and we want to know what will the vapor pressure be at a different temperature. So if we have the vapor pressure of ethanol at 20 degrees and that's 2.9 kilopascals, if the temperature increases to 50 degrees, what will the vapor pressure be? And we're given the enthalpy of vaporization. Well, here's our Classiest iperion equation again. We can write out the values that we know. We know the first pressure, P1. We know the temperature at that pressure. You see I have it here in Kelvin, SI units. We know the second temperature, but we don't know the second pressure. We're given the enthalpy of vaporization and the gas constant, or we know. So, if I use the quotient rule of logs, it allows me to separate out this log of one term divided by another. That's equal to log of the first term minus log of the second. And I do this because I know P2, but I know P1, but I don't know P2. So this allows me to separate these two values. If I rearrange and bring the P1 across to the other side and plug in my numbers, I get a value of natural log P2 is 9.44. So P2 is the exponential of this. So it's 12.6 thousand, or 12.6 kilopascals. So there's an example on the worksheet that you can try.